black hole information problem where you worry about things like the entanglement of the black hole, in which case the thermodynamic description is not the same as the quantum description. The quantum description is a much more fine-grained description where if you're talking about the von Neumann entropy or the entanglement, you care a lot more about those detailed correlations. So the black hole scaling with entropy, the way the black hole entropy scales, I would say, even though it's understood from, well, it's attempted to be understood from sort of a quantum gravity sort of basis, I think it'd be best to sort of think of it as a more classical type of entropy. It's not necessarily at every state following the von Neumann entropy. Yeah, maybe I don't know.
Okay. So, but if I now look at your graph, can you give me some concrete entropy function of something that I should have in mind?
You mean like an exact, like...
It seems to be very different for me to think of, I mean, if I have a gas in front of me, and that's also part of the universe, and think of this as a classical gas, right? Just like the box here. This would correspond to, you know, that would have a lot of entropy. Right? Whereas
but not,
if I have like a black hole, then...
Yeah, and according to generally accepted theory, a black hole has a whole lot of entropy, and he's mostly adding up the entropy of the...
So the rest is like negligible?
Yeah. Yes, compared to...
Including it.
But it's like...
Yeah. It's much smaller. So you would think...
That the black holes might be like this black hole might be entangled with this black hole, and then like they have entropy 0.
Well, so we're not getting into the like how everything's entangled, because we don't know what the like quantum state of the universe is or the quantum state of black holes are.
This is like number, I mean, say all the black holes are the same size. Is this entropy like number of black holes times
the area.
Entropy times the area?
Well, yeah, with the appropriate scaling, but yes, essentially, I mean, each black hole is going to contribute entropy proportional to its area. So you can just add all those up, and that would give you an account. That would be the main part that accounts for your entropy today.
But
we can maybe
that can be made somehow consistent with the fact that the entire universe should be unitary and the whole thing should be 0.
Maybe when we get to my toy model, we can talk about that a little specifically, because it does seem, I mean, built into like the second law. Right, the second law seems not like time reverse symmetric, right? But we believe the underlying laws of physics, like quantum mechanics, to be unitary. And usually you'll have things that look like a second law because you aren't keeping track of everything. So you're coarse graining in a particular way that allows you to not keep track of that information. If the entire universe was a pure state and evolved unitarily, then the entropy of the whole universe would never change. But if you don't keep track of all the information, then you'll have some effective description where you see entropy increasing.
Okay, so I've had this switchy definition before, but somehow so it's which part that you're not keeping track of.
The correlations amongst the black holes.
Okay.
Yes. Maybe one more quick question before I, yeah.
So I'll just to, sorry, maybe it's a kind of question, but usually in standard thermodynamics you already define entropy for confined systems. So to what extent can you define entropy for a system which is not confined? And I mean, for example, you said, okay, things equilibrate and so on, but this really happens because you got some gas in a box, and you got some confined system, and then of course it will equilibrate after some time and so on, whereas if you have no confinement, it will not equilibrate.
Well, so I mean, I guess one thing that makes the story much simpler is the main contribution to the entropy are the black holes. And the black holes are evaporating very slowly. Like their areas, you know, you're not worrying about things escaping the black holes so much. So I'd say there's a good way to sort of keep a decent track of that. If you have a rough idea of sort of population of black holes, you should be able to track these things.
Probably go on, but for example, one of the things that somebody might worry about, I'm sure some people are worrying about, is if we don't know how big the universe is, this is like the Hubble volume adding up all the black holes we think are there. So this is, let him go on, I would say, because this is, he didn't expect to spend 10 minutes on this slide.
And this is a true fact about the universe.
All right, he says it's true.
For certain definitions of these things, you can worry about what other definitions might lead to, but this is something true about the universe.
Yeah, and it's consistent with, I mean, if you don't have a properly defined second law, like you don't include black hole area, then it'd seem like you're just losing entropy into black holes, and it would seem to violate the second law. So you have a more generalized second law. But anyway, maybe we can discuss this more afterwards. Okay, so right, we believe in, this seems to give a nice consistent description. I'm not following the exact time evolution as entropy as it approaches today, but our best description seems to talk about a much lower entropy start. Now, here's sort of the issue and the crux of basic things like, or the main arguments behind things like the Boltzmann-Brain problem. If we were to ask, given our state now, what is the most likely past to explain our state, not assuming that, you know, anything we see describing these previous states are necessarily true, even if what we see seems consistent with this sort of description, which one gives sort of a more likely example? Which one has more trajectories? Well, sort of running the same argument from now into the future backwards, there are far more states with higher entropy. You know, if I imagine all possible states that could lead to the state today, there are far more states with higher entropy that just happen to be fluctuating downwards, going through some weird, unlikely evolution to today, compared to the inherently small number of states that describe some low entropy initial state. This is a basic idea behind the Boltzmann-Brain problem. You can think of this small little fluctuation as a brain popping into existence with the complete description of what I have today, and then I quickly evolve out of that state into something else without any consistency with this apparent evolution I think I have. So that's just a small little summary of the Boltzmann-Brain problem. Oh, there's a slide missing here. Anyway, so I want to transition from that to talking about decoherence. I think it's an interesting question to try to explain the low entropy start. And I want to think about, for small little fluctuations, I want to think about decoherence. And before I go into that more in the toy model, I'll just give a quick little overview of decoherence, which is maybe more familiar to most members of the audience. But I'll just give sort of a quick sort of cartoon look at how it works. The main two parts of decoherence, and I'm not going to focus very much on interpretations of quantum mechanics, but I will say I typically invoke a many worlds or Everett point of view, but that's not necessarily necessary for what I'll be talking about in the future. But regardless, decoherence gives sort of a nice description going from quantum mechanics to or at least part of the explanation for going from a quantum mechanical description to the classical world we see. And sort of the two main ingredients are some entangling interaction. This is going to be in particular between the thing you're trying to measure and the thing that's measuring it. And then the part that allows you to start talking about things classically that sort of make this a good measurement as we understand it, something that looks like what is often called wave function collapse. You're also going to need information lost to the environment. So you'll need interactions with the environment to make it look more classical. So here's how it works. So let's say we started out with the environment in some whatever state it starts out in, and then we have, let's say, a quantum superposition for some particle. You can think of this as a spin, if you like, or a qubit. And then we have the apparatus in some state where it hasn't measured anything yet. You can then have the apparatus interact with the system in the appropriate way to generate entanglement. This is sort of the idea that it is performing the measurement, in which case, whatever part of your apparatus, this is just meant to represent sort of the one little bit in your apparatus which will be associated with whether you measure the particle as being up or down, or 0 or 1, or whatever the measurements can be. So you'll have the 0 state of your apparatus and the 1 state of your apparatus. Okay, and they'll be entangled like this. And then what makes this into a good quantum measure, or a good measurement that we can later think of in our classical world, you'll then have further interaction with the environment, where the environment will start to entangle with these systems, and you'll have some evolving environment that will sort of respect this decomposition in a particular basis. So up to this point, I've written states. All these states I wrote out were orthogonal. 0 states were orthogonal to 1 states. But this environment state, which evolves with time, and this 1 state which evolves in time, will not necessarily start out orthogonal. And they'll be key in sort of how how the system evolves and how you lose coherence that you initially had in the first state. So if we really want to, you usually can't, it's sort of the important feature of decoherence is that you can't keep track of all the degrees of freedom of the environment. If you could, then you might not really be able to say that anything looked classical. You sort of see all the correlations that keep, that preserve the information of the initial coherence. So you're going to inherently have a description where you are tracing out the environment, where this is the state of the full everything, and you trace out to get some reduced density matrix. That density matrix will have can have off-diagonal values, and that's based on whether or not those two states I was mentioning earlier were orthogonal or not. And for this to be decohering properly, there'll have to be an evolution where these off-diagonal terms are dying off, and you're left with just these amplitudes squared. So you go from having to describe things using quantum superposition and having to describe probabilities using the Born rule, to then you can just talk about classical probabilities. You don't have to worry about any coherent mixture of the two. You can talk about these two states sort of separately. And this is the idea that decoherence is happening. And in particular, the special basis where this is happening is called the pointer basis. It is determined based on the interactions with the environment. We'll sort of pick out this particular basis, and then you can say that this measurement occurred and I measured up for spin along the z-axis or down for spin along the z-axis. Yeah, so just summarizing, again, some of the key ingredients. Sort of one sign of decoherence are the diagonals dying off, but I do want to sort of comment that that doesn't give you the full story. You can have, matrices are always diagonalizable, and just because you have some description without diagonal elements doesn't mean you're seeing decoherence happen. So there are better ways to assess whether or not decoherence is happening, but at least this, in this sort of cartoon picture, this will be the way that I'll talk about my toy model. This lets you sort of assess, is decoherence happening? Are you picking out a preferred pointer basis? Are you admitting maybe a classical description? And to tie things in together to my previous description, and here now I mean von Neumann entropy specifically, I'm calculating the entropy for the reduced density matrix. This will be accompanied by an increase in entropy in this reduced system. So that sort of goes nicely with the discussion before, where if you are sort of compounded with the transition from quantum description to classical, you're also following the second law and increasing entropy. So now I want to start talking about my toy model. It's a very simple toy modle, and it's one where...
It's the simplest toy model we've seen so far.
Yes, it is very, very simple. It seems almost silly how simple it is, but I think it seems like you could still sort of extract sort of interesting things to say out of it. Or at least I hope I can convince you that there's potential for some interesting statements. So this very, very simple model is composed of just 8 qubits. Right now I've split it into system and apparatus like this, but for the time being I'm just going to be focusing on 1 qubit. It's sort of, in the future I'll be analyzing what happens to the 2 qubits more. So it's a very small system. It is finite. It is sort of very reasonable scale to talk about because it's so small. And now let me talk about sort of, even though I drew this cartoon, I should explain a bit more about the dynamics and how this thing evolves and the initial state I chose for it. So I'm working with a time-independent Hamiltonian. The full evolution is going to be unitary. The entire state is going to start in a pure state, the state of the environment plus everything else. And I've, an important property of finite systems like this is you're going to go through Poincare recurrences. And because I'm interested in the full behavior of the system, I sort of just picked out very convenient recurrence time. So there's exact recurrence every 256 time steps. And notice I'm working in some dimensionless units, so you can throw in h bars to get seconds and joules, but I've guaranteed this. You have recurrence guaranteed every 256 steps or less. It'll turn out in a lot of the cases I would consider, often multiples of 256 will also be recurrence times. So that'll be nice because I sort of have an idea of what the system is doing for all times. And then I should talk about the energy eigenstates. So I can, once I've specified to you the Hamiltonian initial state, then that completely will specify how my system will evolve. Instead of actually writing down a Hamiltonian, I tried to pick out energy eigenstates that worked well for me. So in general, the energy eigenstates can be whatever superposition of states in the computation basis, or the basis of things just being in zeros and ones, unentangled states. And so I specifically chose a set of eigenstates that have a lot of entanglement. If you were to trace out everything but 1 or 2 qubits, they would always appear maximally mixed, or maximally entangled with something. These are the states I chose, and then all I have to do to find the evolution, which is fairly simple, is just find the initial state, write it in this basis, and then follow as it sort of trivially evolves. Although, in my opinion,